Thank you, Bridget, and thank you, everyone, for having me at POPL. It's a great honor. So over the past 14 years, myself and my team have been working on finding bugs and vulnerabilities in software through program analysis type of techniques. And regardless of language that we work on, whether it's C, C++, Java, PL SQL, JavaScript, Python, what we find is that the type of vulnerabilities that you see are the same over and over again. So we're seeing exactly the same patterns. And this is what led us to start looking into why is this really happening? It's not like our developers want to write software that has bugs and vulnerabilities in them. It's more that our programming languages are not providing the right abstractions for them to write secure code. So in this talk, we take a data-driven approach to be able to define what is a secure programming language. I'm Cristina Cifuentes, and this is joint work with Gavin Bierman for Oracle Labs. Now, before I go into the talk, just to let you know, this is just a line of research at Oracle Labs. It doesn't really imply that we're developing a product, and all of the opinions expressed in this talk are my own. Okay, so we took data from the National Vulnerability Database. The National Vulnerability Database keeps track of all of the reported vulnerabilities that have been exploited on software throughout the years. We focused on 3 different years, 2013 to 2017. And when you look at the data, just focusing on buffer errors, what you find is that there's 5,899 exploited vulnerabilities, right, over these 5 years. That equates in the order of 3.2 buffer errors, new ones being exploited on a day-to-day basis for each of the days in the last 5 years, right? This is significant, a large number of issues. And this is the #1 type of issue over those 5 years. We then looked at #2, injection type of errors. And with injection type of errors, 5,851 exploited vulnerabilities, very close to buffer errors. And here, when we refer to injection errors, we're really referring to various different types of injection attacks, like cross-site scripting, which is the most common and popular one, followed by Sql injection, OS command injection, and so on, right? So this is also in the order of 3 new exploited vulnerabilities on a daily basis. And the #4 category ended up being information leak. This is a category that is actually rising over the last year with 3,106 different issues, so in the order of 1.7 new issues on a day-to-day basis. It's still a very significant number of issues. Now, if you combine all of those 3 categories, what you find is that you have 53% of the vulnerabilities reported in the National Vulnerability Database equating to just these 3 different categories. And that's significant. Imagine all of the time that developers could save and all of the innovation that they would be developing if they didn't have to be fixing all of these vulnerabilities that are happening on our software. And the most important thing is that these 3 different categories are really something that are in the realm of programming language design. We could actually introduce concepts to prevent those type of issues in our languages. And so, you know, new year, we went, oh, let's look at the data that has just been published for the whole of like the 2019, combined it with 2018. And what are we seeing? The numbers are just increasing, okay? And for the first time ever, injection errors are the highest number of issues that are being exploited, okay? For both of those years. 5,970, look, this number is larger than the earlier 5 years, right? This is in the order of 8 new exploits happening on a day-to-day basis. So we've gone from 3 to 8, you know, getting worse, right? Buffer errors are now #2. But still, the numbers are quite high, 4,651 in the order of 6 per day, still very high and even higher than in the earlier 5 years. And then our information leaks are still number 4 in the category, 1,980, which is again higher than the earlier 5 years. And this is in the order of 2.7 per day, right? So significant number of vulnerabilities being exploited. The number of vulnerabilities are going up and up because there's more and more exploits being reported in today's world. And for these last 2 years, these 3 different categories equate to 45% of all of the vulnerabilities in the National Vulnerability Database. Still, same premise, these 3 categories are really in the realm of programming language design, and that's what we want to focus on. Now, the most depressing thing is that these type of issues have been known for a long, long time. Buffer errors were first exploited in the Morris worm back in 1988. So over 30 years ago, we've known about buffer errors. Cross-site scripting exploits were being exploited since the 1990s. Sql injection fully documented for people to be able to understand it and reproduce it since 1998, right? So more than 20 years. We've known about a lot of these issues for a long, long time, yet we're seeing them very heavily in all of the exploits that are happening today in our world. So let us look at a few examples of these vulnerabilities just so that we're all on the same page. And I'm going to start with buffer errors. And the idea here with buffer errors is that we want to look at different pieces of code to understand like what type of issues are happening. In this particular function, host lookup, we have a statically allocated array, host name, that is going to hold a name. It's a character array of 64 characters. And what this routine is going to do is that it's going to take a supplied name, and then it's just going to copy it through the string copy routine onto that particular buffer. Okay. Now, the buffer error in this particular case is the fact that when you do the string copy on this last statement here, you're going to copy across the name that is coming from this HP get host address header information. It's going to be stored into the host name, but there's no actual check as to whether all of the characters that we have on our HP name are actually going to fit into host name, right? So we may end up overflowing this particular array and then damaging all the data that follows in memory this particular array. Now, here's a simpler example, less code. In this case, we're looking at a heap-based buffer overflow. So you have a very simple main method. It has a dynamically allocated buffer buff. And in this particular buff, we're allocating it of the size buff size. And then what do? We're doing a string copy from argv1, which is data that is coming from the user. We're not checking how long that particular string is. So again, we can overflow the buffer in this particular case, and we end up with a buffer overflow. Okay, let us look at cross-site scripting. And in this particular case, we're looking at JSP code, a very small fragment. And with cross-site scripting, what happens with this vulnerability is that the attacker is going to inject malicious code into an otherwise benign website, right? And because the website is going to execute the code, there is where the actual injection can happen. So in this particular piece of JSP code, we're going to take an employee ID through a HTTP request, and that's our EID. And then we're going to display it back later on. And you have that in this particular statement. So the problem here is that without actually doing any sanitization of EID, we may have statements or some execution of code that is going to be executed by the website, and you end up with your cross-site scripting type of issue, right? So this is known what is. This one is called a reflected cross-site scripting. And there are other types of cross-site scripting, for example, stored cross-site scripting. And in this particular case, you're going to have a piece of code, again, JSP code, you're going to have a connection statement, and you're going to have an execute query. And see that when the query gets executed, we're just getting access to a particular name, and then we're going to display that particular name. So this particular piece of code is a vulnerability only if when you store the data in the database, that name, when you stored it in the database, if the name came from user accessible inputs, and if it was not sanitized, we're pulling that name from the database and we're just displaying it back to the user. So again, we can have cross-site scripting in this case, but through the storage in a database, okay? So the issue is on that particular last statement. Now, what about SQL injections? There are different type of injection, type of attack. In this particular case, we have some C# code, and we're looking at a user that has been authenticated, okay, on the first statement. And what we want to do is to dynamically create an SQL query. And you can see the select statement that we have there, and we're making use of some item name.txt data that is actually coming from the user. Then later on, we're going to get the information and we're going to display that, right? So the query itself is the issue that we have with our SQL injection, that when you execute that query, any data that came from the user needs to be sanitized because you may have had meta characters listed in that data. So with SQL, you saw how the particular dynamic statement was created, right? If you have like a dash and any other meta characters, you could actually have the equivalent of just select star from items and end up displaying everything, because you may end up on the right-hand side with a true statement, right? Like A equals A. Or when you have SQL APIs that actually allow you to concatenate multiple statements, if you are using like a semicolon, an attacker may use a semicolon, then have a drop tables type of command, you would end up executing both of those statements, right? So that is why sanitization is needed for the particular query before it gets executed. Right? And last, let us look at our information leak. And with information leak, the issue that we have in this piece of Java code is that information leaks tend to happen because you're making available sensitive data in an untrusted environment. And they can happen through various different forms. It could be that you're displaying information into a log. It could be that it's being exposed to an environment variable, or it could be a Java runtime exception where you're displaying this sensitive information, and there's many other forms, right? The most common one, however, is through logs, that you may be displaying and storing sensitive information in your logs. And clearly, in today's cloud world, this is something that everyone, that is involved in cloud development is very sensitive about. You need to be very careful about leaking information that way. So in this piece of Java code, we have at the top, we have this object. This particular object has information about a particular user, and we're going to store information about that user, the location information. Location information is considered sensitive data, right? And then you notice that in the code there's an exception. The exception is actually going to go and store information and display in the log all the information that it has for a particular user, but hence notice that that's also going to display the location information for that user, right? And hence is doing an information leak through logs. All right? So those are just some examples, just to give you an idea of the type of vulnerabilities that we're talking about in today's talk. So now let us get into the actual talk itself. So what do we consider mainstream languages, and how do these vulnerabilities relate to those mainstream languages? Now, we took the data for the past 10 years, well, actually up to January 2019, and we used the TIOBE index. You could use any other index, but the idea here was to be able to determine which languages are considered the top mainstream languages over a long period of time, 10 years. And the languages that are the most popular ones, according to TIOBE index, are Java, C, C++, Python, C#, PHP, JavaScript, and Ruby. Okay? So from these languages, we then went and mapped these languages onto the 3 different categories that we're interested in preventing vulnerabilities from them. And what you can see here is that in order to prevent buffer errors, there are several languages that provide that functionality, right? Like Java, C#, JavaScript prevent buffer errors through the fact that they're managed languages, right? You have the PHP language through library support. They actually prevent injection type of attacks. We found that both the Ruby language and version 1.1 of JavaScript made available support for both how to prevent buffer errors as well as how to prevent injection type of attacks. But notice that that functionality was dropped later on in JavaScript. And then you notice that this box at the bottom, like information leaks, is empty, right? And the worst thing, like there's no language in the middle, right? That could prevent these 3 different types of very common type of issues that are prevalent in today's code. So our premise is that a secure programming language is one that can provide first-class support to prevent these 3 different, very common type of vulnerabilities in today's world: buffer errors, injection attacks, and information leaks. And during the rest of the talk, we're going to look at some of the security abstractions that have been put in place, and we're going to talk about them in terms of 2 different axes. There's the performance overhead axis. That is very important to developers, of course, because you may have a security abstraction that is very secure and good to write the code, but if that abstraction is going to create a high performance degradation in your program, it's probably an abstraction that is not going to be used for all types of code. Right? The other thing that we need to consider is the cognitive load. And this is because if the abstraction that you create is an abstraction that is going to be very hard to understand or very hard for the developer to get it right, it just makes it hard for them, right? And again, it may end up being an abstraction that provides you security, but then it's not going to be widely used. The language will not become one of the popular languages, right, in today's world. And of course, it's very clear to see that ideally you want an abstraction that is not going to create a lot of performance overhead, and at the same time is going to have a low cognitive load so that it's easy for developers to use and performance overhead is not going to be impacted in your applications, right? But that's pretty hard to get to that point. Nevertheless, that's the ideal case. Okay, so then let us look into language support for addressing buffer errors. And we all know that the problem with buffer errors is the fact that we're using an unsafe abstraction. The unsafe abstraction that we use is the fact that we ask developers to manually manage all of the pointers in languages like C and C++, right? And you saw from the data tons of vulnerabilities that are exploited as buffer errors. Now, why is this high cognitive load? Okay. It's high cognitive load to get it right. It's low cognitive load to just write any code and then it gets exploited, right? And that is the problem. right? That the data is showing that we really are not able to write programs that are correct if we have to manually be managing our memory through pointers. Okay? So what are examples of safe abstractions? Here we have two different abstractions, and I'm only going to focus on one of them. So very briefly, managed memory. It's an abstraction that all of you are familiar with. You know, first introduced in Lisp, widely being used in a lot of languages today, Java, JavaScript, Python, and so on, right? And this particular abstraction is an example of an abstraction that provides like no cognitive load whatsoever to the developer. Because me as a developer, I don't have to do anything about managing memory. It's all being done in the runtime for me, automatically. I don't have to think about it. It's the best example of a low cognitive load type of abstraction, right? And notice in this slide that we put it as it provides some performance overhead. And it's not that I'm saying that Java is slow. After all, I do work at Oracle. Is that relating to your application domain, the abstraction may actually introduce some performance overhead to you, right? If you're working in the embedded systems market and you have like managed runtime, garbage collection happening, and so on, you know, it doesn't always work compared to languages like C and C++. So that's what we're really saying there. So now let us focus on a different type of abstraction, lifetimes and ownership being provided in the Rust language. And the Rust language, you know, new programming language in the past, 2009, so for the past 11 years, it has been around. Now, this language is really focusing on systems programming. So again, it's on the same level as C++, like it aims to be focusing on those type of systems type of applications. It has no garbage collection. And what is novel about this language is that they're preventing buffer errors and a lot of other issues as well through the introduction of lifetimes, the introduction of ownerships, introduction of lifetimes and borrows in their type system. So everything is being done at compile time. And it's going to tell the developer that there is an issue in the code. Now, through ownership, this is a concept that was already being used in C++. So a particular resource can only have one owner, right? And then through borrowing, we're going to see a few examples later on, but through borrowing, the concept here is this idea of we're going to restrict what you can do with your pointers. So there's two ways that you can borrow like a reference to a resource. You could have a shared borrow ampersand of a particular type, and that means that I can share with you, you, and you. However, you cannot mutate it, right? So multiple shares, but no mutation happening. On the other hand, I can have a mutable borrow, so ampersand mute of a particular type. And in this case, we can mutate it, we can modify, like the reference that we're pointing to. However, we cannot alias it. And what these two different types of borrowing do is that you can never have like one particular reference that is acting as both at the same time. So it's either shared or it's either mutable, but it's not both. And that prevents a lot of the issues that you see in a lot of the different languages related to buffer errors and other types of issues. So here's a small example. Let's say that you have a main function. In your main, we're going to have variable I that we're going to give it the value of 3. And notice that in this particular code, there's different lifetimes for different sections of the code. Variable I itself has a lifetime that ends at the end of this particular main function. Within this particular block, we have another lifetime. We're going to have a borrow1 that is going to get a shared borrow on I, and its lifetime ends here. Okay? Because we've borrowed, we can print it, that's fine. We print the value, that's no problem. We have another lifetime happening here on the second part of the code where we have a borrow2. We're getting a mutable borrow on I, and that means that we can actually modify it. So now its value is 5, and that's fine. Okay? So this piece of code, is never going to throw an error because we've used like shared borrows and mutable borrows correctly in different lifetimes, okay, against different variables. However, if we do a simple modification of this code and we just have, let's say, a borrow3 where we have a mutable borrow on I, we modify it, that's fine. We're going to display the modified value, that's fine. And then we do a shared borrow on I, the compiler is actually going to throw an error for us. And the compiler is going to tell us that we cannot borrow I as immutable because it's already borrowed as mutable in the same lifetime. Because notice the lifetime starts here and it ends here, right? So statically, the type system is able to tell us, hey, you're going to have an error, you cannot do this, and therefore you need to change your code, right? So it's a great way of being able to have support in the language through type system, even better, right? Developers actually are told at compile time about any issues that they have in the code, and they can go ahead and fix this code. Now, Rust actually provides memory safety guarantees, not just on buffer errors, but a lot of other types of memory-related type of issues, like your double freeze, your null pointer dereference, use after free, and so on. Okay? And it also provides support for unsafe. And this is the fact that in practice, there's billions and millions of lines of code that have already been written in legacy languages like C, and you need to interoperate with those languages, right? So unsafe provides a way of being able to go and talk to all of your C code in such a way that you can do foreign function interface to it, and you can implement also like dereferencing of raw pointers if you really, really need to. And notice that some of Rust internal libraries actually make use of the unsafe feature. So overall, with Rust, like here the idea was like, let's introduce some concepts into the type system. They make use of ownerships, they make use of the borrow concept and lifetimes to be able to keep tracks at compile time errors that prevent you from having buffer errors and a lot of memory safety type of issues in your code. Notice that it does provide support for unsafe, which means that you as a developer, if you need to interoperate with existing legacy C code or C++ or whatever, you need to ensure that the way that you're interoperating with that code is not going to void your memory safety guarantees by introducing some code that is coming back from the C native code. All right, but very, very good support, and like very exciting to see like new abstractions in this space. Now, let us look into injection type of attacks. And with the injection type of attacks, the unsafe abstraction, of course, is the fact that we have manual concatenation of strings happening in our languages, right? And then developers have to do sanitization over that code. You see it in a lot of languages, and everything gets passed as a string, and then we go and execute like our query or anything as a string, and no checks whatsoever. We're expecting the developer to do quite a bit, right? And we have very large applications that are written in today's world, and it's just unreasonable to expect that the developer is going to be able to track all of these in their head through many different methods to determine, oh, actually, it came through something that is user accessible, and by the way, no one has sanitized this data. Now, the safe abstraction that we can use in this particular case, I'm only pointing two of them for this example. There's LINQ to SQL, which is language integrated query, which is available in the .NET framework. It's an abstraction that very specific to SQL, but under the hood, what it's doing is that it's making use of the right way of invoking and checking for all of the code, SQL-related code, when you're putting together dynamic queries, right? And it works well in this environment. Again, it's specific to SQL, and it supports most of the SQL type of queries, not all of them. The one that I'm going to focus on is taint mode, because taint mode, both available in the Perl and Ruby languages, it was aiming at providing like a more general way of preventing injection type of issues in different languages. So with the Perl language, the taint mode abstraction was first introduced in 1989 in version 3 of Perl. And the idea here was to track any data that was coming as user input or from any inputs was considered tainted data, right? And then Perl had a runtime system. The runtime system was keeping track of how that tainted data was moving around throughout the application that was being executed, right? Now, versions 3, 4, and 5 of Perl actually have like a lot of support for tainting in terms of what are default values that create tainted data for you. All of the command line arguments, of course, by default, they're coming from the user, they're tainted, environment variables, locale information, and so on, right? Further, the runtime system, its aim was to be able to track like the tainted data through direct and indirect uses of this tainted data. And it was tracking everything that was going to reach commands here, commands that invoke subshells, right? And also any command that modifies files, directories, or processes, because any of these are security sensitive, of course, and you want to ensure that tainted data doesn't get there without it being sanitized in the right way. Notice, however, though, that because of the way that the implementation was done, and because of trade-offs that were needed, there were some exceptions in this last case. So when you had tracking of tainted data through commands, it was not tracked to print and syswrite methods themselves, okay? And we'll see in an example why this is important. Now, the Ruby language actually went a step further, and it said, okay, we're going to take the same type of abstraction that Perl has, which is level 0 and 1, right? And we're going to go further and have other levels. We have level 2 that is going to prohibit loading program files from globally writable locations. And it also had level 3, whereby any newly created objects were considered tainted, right? So the abstractions were trying to provide more and more security. Of course, some of it does make it a little bit harder to work with. Now, let us look at this very simple example. And in this code, we're not making use of any of the safe levels in Ruby, but this is a modification of some Ruby code. So let's say that we have this CGI form. In this CGI form, we're implementing an arithmetic calculator. And the idea was that the user can input different type of arithmetic expressions. So I can input like 3 times 5 minus 20, and it's going to display for me the answer to it, right? So we're taking in this CGI expression an expression, EXPR, as a string, right? And notice that we're going to evaluate that expression so that if I input 2 plus 3, it's going to then display that value for me down here, okay? Now, you would have noticed that because we're just evaluating like any expression that is going to be input through this form, a malicious user may actually not input like a valid arithmetic expression. They may be inputting something like system remove star. And this code, we just go and execute it, and now we're removing all of the files in our file system, right? So clearly that's an issue. Now, how would you write this code correctly using Ruby? So the idea here was to first state like what safe level you're working on, and we're working with safe level 1, which is the same level as Perl. We're taking in our expression, and notice that in Ruby, we have a way of untainting tainted data. So if we check, we do the equivalent to sanitization, what type of characters are allowed, which ones are not allowed, then we can say, okay, this particular expression that the user input doesn't include some of these statements, therefore we're fine, we're going to untaint it, so it's safe to actually evaluate it. And that's fine, right? So that's good. But then what happens if you actually modify this code and you do something that is just about the same, right? You have your expression, you're untainting it, you're evaluating, that part is fine. What happens if I'm then displaying that expression through a print statement? In this particular case, notice that the untainting was untainting for being able to evaluate an arithmetic expression. The runtime system is not tracking anything that makes it to a print statement, and therefore, in this particular case, I have no warning that something malicious could happen. And what happens is that I could actually have a cross-site scripting attack happening at this particular last line, because the user could have had some malicious code that gets executed in this particular statement, and there was no tracking of that, right? And that was just purely because of an implementation trade-off that needed to be done. Okay? So now to summarize, taint mode is one of these abstractions that does help the developer in terms of being able to prevent various different types of injection attacks. Depending on the safe mode that you were at, you would have different type of errors being thrown at you. If you have tainted data being used in particular places, the system would actually tell you. It does have like some limitations, as we saw with the last example for cross-site scripting, and that means that this type of abstraction, even though like it works for certain types of applications, you know, it's an abstraction that is not going to work well in today's cloud worlds, and there is where we have limitations and the need for new abstractions to be developed. But nevertheless, you know, like very good concept, a way of hiding a lot of the implementation in the runtime, and the user not having to do a lot of it manually themselves. Okay, and now let us look into information flow. Information leaks. And with information leaks, of course, the unsafe abstraction is the fact that we're manually tracking sensitive data, right? And this sensitive data is becoming available to untrusted sources. There are two different types of safe abstractions that we could make use of that I'm going to highlight in this particular talk. On the bottom right-hand side, we have like policy annotations. This has been available in Chief, also in Fabric. And with this abstraction, like the main cognitive load that we see with the abstraction is the fact that the developer needs to write all of these annotations, right? Some of them can be inferred, but nevertheless, there's quite a number of annotations that need to be written. And when you have programs that are millions of lines of code, this makes it very hard on developers to be able to have to write all of those annotations. I'm going to focus on policy agnostic programming, which is an abstraction that has been used in a few places. This particular work was done by Yin Yang as part of her PhD thesis in terms of the Jeeves language, which is just purely implemented on top of Python, and the Jacqueline framework for the database side of it. And so what's interesting about this type of work is that with policy agnostic programming, you're trying to move all of the policies away from the actual source code so that you have a separation between policies and the rest of your code, right? And then they're making use of this concept of faceted values to be able to track sensitive and non-sensitive values throughout the application. And this gets tracked by the runtime. The fact that they also looked into the database side of things means that you can have very realistic applications that are actually, you know, like web applications where you can also store information into your database and be able to work with all of it in a way that where you can demonstrate how to prevent information leaks. Now, faceted values is this abstraction where you use it wherever you have sensitive values. And if you have a sensitive value, you actually want to keep track of both. What do you do if the policy says that you should show the sensitive value, and what value should you show if the policy states that for you, we should show the non-sensitive value, right? And so that would be like the type of faceted value that we have here in normal code. You can extend it to a database as faceted records, keeping track of the same type of information. And for simple implementation, rather than, you know, let's develop like a new database, you know, this was an academic prototype after all. The idea was that you can have two different records to keep track of the information. And here, like FID was my faceted ID. So both of these records relate to the same faceted value. Here's when your policy is true, I display the value of S. When your policy is false, I'm going to display the non-sensitive value, whatever that value happens to be, right? And if you had like a very simple type of application, like a social calendar application, and you had, you know, like Alice wanting to have a surprise party for Bob at 7 p.m. on a particular day, then you want to ensure that all of the people that get invited will end up seeing surprise party in their calendar application. However, Bob and anyone else that is not invited to the party, they should only be seeing like there's a private event and not actually know that it's a party, right? And their implementation made use of all of this other support, whereby here you have everything is going to be done through the context. So the runtime is keeping track of the context. It knows who is like the one that is going to be using this calendar application. If it's Bob, based on context, it would know that we need to just let him know that it's a private event. If it's someone else, depending on who they are, then it would show some other value, right? One of the key facilities that was available is the fact that you have all of these different type of select statements, right, that are going to be transparent to the developer, because a lot of it is done under the hood. So you're using the same standard type of SQL API that you're used to. However, under the hood, it's actually introducing some extra values for you so that it keeps track of what do I really need to do to show the developer, to show the user the right type of information, right? And they tested it with 3 different types of applications. Of course, they found that the amount of code gets reduced in the application because you're moving away the policy code. Being able to audit the code, easier and simpler, of course. Their implementation was an academic prototype, so it still had like some performance overhead. Some of it can be reduced if anyone was going to implement this like more in production mode. So to summarize, this is an abstraction that provides a way of dealing with prevention of information leaks in such a way that you're keeping track of the sensitive and non-sensitive information throughout the program through faceted values, and at the same time the policies are being separated from the rest of the code. So let us recap what I've been saying so far. We mentioned that there's top mainstream languages, variety of these languages that you may be using. Clearly, like developers are using these languages in today's world. Our premise is that a secure language is one that is going to provide first-class support for 3 main categories of vulnerabilities: buffer errors, injection errors and information leak errors, and it's going to prevent them. And it's very clear that today's mainstream languages do not provide support for our developers in writing correct type of code using these three categories, and therefore our mainstream languages are not secure languages. Now, in this talk, I only mentioned some abstractions. I talked about, like, focus on the three that are with the red box. I didn't talk about information flow, but clearly that's another type of abstraction that could be used as a solution for preventing injections and information leaks at the same time. Wouldn't it be great that in the future there were a lot of other abstractions available that we could choose from and see which ones work well and better for the particular language that I'm developing? And wouldn't it be great that your next language is a secure language that actually prevents a lot of these issues so that developers can be freed from having this type of errors in their applications? Now, if that was going to happen, imagine in the future this actually happened, are we done with vulnerabilities? And the reality is that, of course, not, right? These vulnerabilities, there's other types of vulnerabilities that are also prevalent in today's code. Two of the main type of ones that relate to programming languages are resource management type of errors. So your use after free, double freeze, memory corruption, typecasting errors, worker termination errors, they're all examples of resource errors, resource management errors. There's also your race condition errors, right? Due to concurrency, due to time of use, time of check, right? These type of errors are also in the realm of programming languages. And very briefly, there have been recent projects that focus on aspects of resource management type of issues. So for example, in Rust, you have support to prevent, like, your use after free, your double freeze. That is actually part of their language. But you also have this new language, Project Verona, from Microsoft, where Matthew Parkinson made a first public presentation last November. The code was actually open source, like, in the last 2 weeks. And amongst, like, their three main core ideas, the one that is going to help with resource management is linear regions. They're looking at if you have collections, rather than keeping track of each individual object as separate, you can have, in a collection, you can have a linear region, and you can keep track of all of those objects at the same time, right? So whenever you're outside of a region, you can access that memory. Also, you can access memory once the region has been freed, so hence you're preventing some of these common type of issues. Now, there has also been some work relating to data races. So with race conditions, like all of the work that we've looked at in programming languages focuses on the data races. And both Rust and Project Verona have support for being data race free, which is excellent, excellent way, like, you don't have to worry about it, right? There's also been work in the Pony language. Sylvan Klebsch started doing this work while he was at Imperial College. The work has continued. He's now at Microsoft Research, and the work keeps on going, right? Here, he's using actors for concurrency, but key to his design was the fact that he wanted the type system to be data race free, which is, again, great way of having a way of providing concurrency to users, but at the same time ensuring that the type system is checking that you're not going to have some of the common type of errors that happen when you write concurrent code. The language also happens to be memory safe, and they keep track of reference capabilities on the paths to different objects, different types of reference capabilities. Of course, there are other practical issues that you need to consider, and with these issues, you always have interoperability with foreign function code, right? What do? There's millions and millions of lines of code. It's not feasible to rewrite all of this code if you need to interoperate with it. Some of the solutions that we've seen are different approaches. One of them is like being able to use multilingual compilers and runtime environments. For example, Thomas Werthinger with the Graal VM has one runtime that supports multiple languages. It's much easier to be able to do the foreign function interface and keep track of safety guarantees that way. There's also been like work in Project Verona, where they have compartmentalization of legacy code, and the compiler actually knows this. And the fact that the compiler knows this, it helps in trying to prevent issues that may creep in into your safe code because you were using some of the unsafe legacy code, okay? And that is one of the differences with Rust, in that Rust doesn't do that at compile time for you, okay? There's also like the complexity of modifying a VM. I mean, like no one, would want to do that, especially in academia. But there are other ways of doing it, right? Like you can have compilation that preserves security properties via translations, but don't actually implementing all of those changes in the VM itself. Now, with 18.5 million developers worldwide, I noticed that 40% of those are hobbyists. They didn't necessarily come through like university degree, they didn't get like PhDs and so on. Security is not just for expert developers. And we cannot keep calm and carry on programming the way that we've been programming in the past. It's really time to introduce security abstractions into our language design. Thank you.
Yeah, thank you very much. I see a number of hands, so we'll start with questions, and I'll start with Adam since he was first.
You were presenting lists of different categories of security vulnerabilities that programmers should worry about. And then one concern many people have with that kind of list is we wonder if we left out something important. And also we might feel like we need to build a different mitigation for each one, which leads to a kind of complex platform. There's an interesting connection with another subject studied at POPL, which is proofs of functional correctness, which tend to have the side effect that if you prove a program functional correct against almost any spec, then none of those vulnerabilities can be there because they perturb the program behavior so much they're going to wreck any goal that you have. How do you see the potential rising importance of functional correctness proofs to more secure programming?
Right, yes. So with functional correctness proofs, it's been changing over time, right? And part of the problem in the past has been like, who writes these proofs? You need to have like very specialized developers that can actually prove them, right? And there's different levels of proofs, right? Like you can have like fully automated ones, or you could have others where you actually need to do like some more work yourself. And it has always been hard, like, do you have like a team that can actually do this for you, working along with your developers so that then everything works well, right? Of course, like there have been like some languages that have tried to automate some of these proofs, and that's like a great step, because then we're not asking the developer like, oh, you go and do the proofs and then we check the programs and so on. No, like the actual language itself is actually checking some proofs for you. For example, the Wiley language is doing something like that, right? So I think it's a great step towards like the right place overall.
First over here, and then I'll come back. And then I'll check Slido.
Thanks very much for your talk. So you said towards the end, kind of what happens if we do fix these problems that you've identified. But I wondered, what do you see happening if we don't take your advice? I mean, we don't fix these. We just carry on using unsafe C. Is it just a matter that in a few years you'll be still giving this talk, but with slightly bigger numbers at the start?
That's what the trend currently is, right? And actually, just like yesterday, I checked the TIOBE index for what was like the language that was considered the language of the year for 2019. Guess which one? C. And you go like, oh my God, why is this happening? In this particular case, it's because of IoTs You know, a lot of people are using C, and you go like, oh, right, like this language is now becoming even more popular again, right? Not just like for systems level code, but now for IoTs. And I mean, the IoT space is clearly one of those spaces where it's an opportunity. We could actually be developing like safer languages that don't provide like high runtime overhead, right? Because they're tiny devices and so on. But it's an opportunity. You don't need to develop like huge libraries to be able to deal with it, right? And I think, you know, like we really need to start changing the way that we write these languages, because otherwise more of the same keeps on happening.
Okay. Since Dominic has been raising his hand for quite some time, I'm going to give him the mic.
Thank you. So thanks for your talk. So one security abstraction that you don't mention, and which is also used in Pony, for example, is capability-based security and related old ideas like principle of least authority and that kind of thing, where you try and limit the authority that components have to the minimum. So can you comment on that, or do you?
Yeah. Like there's a lot of different abstractions that I didn't mention. We were trying to focus on abstractions that either we could find in mainstream programming languages, or ones where we saw like, oh, there's a prototype that seems to be working well, like showing, you know, like in real languages, in real in real applications that it worked well, right? Like with capabilities, it has always been a little bit tricky in the sense that you're raising the level of abstraction one level higher, and then it's like, who do you give the capability to, right? If you give the capability in the wrong way, then you still end up with security issues happening in practice. And what we were trying to find is like, has anyone actually looked into how to prevent giving away capabilities in the wrong way? And not much work has been done in that space that we could find. Although like we are working with a professor at Macquarie University precisely on that point, like how do we embed capabilities? How do we do it in such a way that they get checked for you in certain cases, so that it makes it easier to ensure that you're not going to make available the capability in the wrong way and therefore void everything that you were trying to protect. Of course, there's other approaches as well, yeah. But again, yeah, that's one that if you look at that next level of abstraction and that gets solved, it would be great. You know?
Okay, so maybe we'll take one more question. And since Phil has been raising his hand, you get the last word.
Oh, thanks. Very nice talk. You skipped very quickly over link, but it was the only thing that was in the sweet spot of low overhead and low cognitive overhead and low performance overhead. And of course, it's near and dear to my heart because at Edinburgh we have links, which is very similar to LI and Q. And that works great for presenting injection attacks. It works great for integrating your database with your programming language. But you also talk about cross-site scripting. It's less clear to me how well link or links would work with that. Could you say something about that?
Yeah, well, LinkQ was really focusing on SQL type of injections, right? So it wasn't focusing like on how to prevent your cross-site scriptings. And that's why like it's not like a general solution. It's specific to SQL injections. Okay? Yeah. Trying to have like a general solution for cross-site scripting has been hard. And you saw like not even with taintable you could fully do it because of trade-offs in the implementation, how to ensure that the runtime wouldn't be too slow if you're starting to track too much information, right? And you also have the problem of indirect tainting and implicit tainting and so on. So it makes it harder like for cross-site scripting. But if you look at the raw data, cross-site scripting, amongst all of the injection issues, cross-site scripting is the one that is most widely being exploited these days. And its numbers have been going up and up and up throughout the last years. So it's clearly one of those that it would be good to have a solution for it.
All right, well, thank you very much, and we'll break for coffee. Thank you.
Thank you.